afternoon and very warm welcome to the Oxford Martin School, the continuing seminar series on climate change, what's happening and what we can do about it. I'm Ian Golden, I'm the director of the Oxford Martin School, and I'm delighted to see so many of you, and particularly this evening to have two really great colleagues of the Oxford Martin School who've worked in our Oceans group, Oceans for the 21st Century, which was a group which really took forward our understanding of oceans. And that's because, amongst other things, the leaders of this group are such great academics. We're going to have this evening David Marshall, who's the professor of Physical Oceanography and the head of Atmospheric Oceanic and Planetary Physics at Oxford. He was, as I said, the co-director of our 21st Century Ocean Institute. He's an expert in the school now, and amongst his many research interests are fluid dynamics in global ocean circulation and the role of oceans in climate. And he'll be joined by Professor Gideon Henderson, who's the professor of Earth Sciences, also the head of the Earth Sciences Department at Oxford. Gideon was the co-director with David of the group on 21st Century Oceans and also an expert advisor to the Oxford Martin School. And his research focuses on understanding long-term climate change and the carbon cycle, and therefore the future changes that are likely to take place. The way this is going to work is that Gideon is going to begin, David's going to be the sandwich in the center of the sandwich, and then Gideon will make some concluding remarks and we'll open up for conversation. So Gideon, you have the floor.
Thanks, Ian, for that introduction. Lovely to see you all here today. How inappropriate to call it Earth when clearly it is ocean. That's a rather cheesy remark, perhaps, to start with. It's an Arthur C. Clarke quotation. And I think maybe that's a cheesy start, but this image makes it more clear that this planet is misnamed. I mean, it should be called ocean, and it's clear from this picture that the surface of the planet is dominated by the ocean. And one of the areas where the ocean dominance is also really pivotal is in climate change. And you see that if you think about the role that the ocean plays in both the carbon cycle and the heat budget of the Earth. These two statistics make that clear. The top 2.5 meters of the ocean contain as much heat as the whole of the atmosphere, and the top 50 meters of the ocean contain as much carbon as the whole atmosphere. So that little skin at the top of the ocean is equivalent in heat and carbon terms to the whole of the atmosphere, even though the ocean is much deeper, and therefore you get a sense of the fact that on long time scales, the ocean really is what dominates the climate system and the carbon cycle and drives it forwards. Now, that's been recognized by many people, certainly by oceanographers, and then more recently by the leaders of the G7. So during the German presidency, the G7 have been in amongst trying to run Greece and sort out Ukraine, also trying to sort out the oceans. And they're working on a document to really spell out what the challenges are to the ocean in this anthropogenic era when we're changing the world so abruptly. Some of the areas that the G7 have pointed to and which oceanographers are aware of as being challenges in climate, in ocean sciences are listed on this list. And don't worry, I'm not going to try and go through all of these. But what I'm going to do is introduce some of these here, and then pass over to David, who'll talk about a couple of them, and then return it to me. So the first title I've got up here is The Oceanic Responses to Increases in Atmospheric Carbon Dioxide, and of course that is the thing that we are directly driving. We're not really changing climate, what we're changing is the carbon cycle. What we're doing is pushing out large amounts of carbon dioxide and causing this steady increase in the atmospheric composition. And it's that, in turn, which causes climate change. So what are the direct impacts of this carbon dioxide increase? Well, if you increase the partial pressure in the atmosphere, some of that carbon dioxide dissolves in the ocean, and you can see that clearly in this image here. Like many of my figures, it's taken from the IPCC report. And this shows you the ocean inventory of carbon which has been added as a consequence of anthropogenic activity. And the oceans consume something like 40% of the carbon that we've emitted. The numbers are down here, so we've burned something like 365 petagrams of carbon, and about 155 petagrams of that have gone into the ocean. But you see that they haven't gone in uniformly. They're spread around with different colours on here, reflecting ocean circulation, reflecting the need to understand the way that the oceans operate if you want to understand and predict future uptake of carbon into the ocean. Now that uptake of carbon that you see on this image is also changing the chemistry of the ocean and leading to ocean acidification. On the top panel here in black, you see the CO2 level in the atmosphere put on top of what's happening to the oceanic CO2 level. So the fact that the atmosphere is going up means that the oceanic concentration is also going up. You can see that the ocean breathes in and out because of temperature changes, but has the same long-term trend towards higher PCO2. And that's in the middle and lower panel causing a change to lower pH, more acidic conditions, and in the lower panel, decreasing the carbonate ion concentration. So this has important implications for ecosystems in the ocean, which we're still really trying to work out as a community. The lowering of pH and the lowering of carbonate ion may actually benefit some species. Those which take up carbon directly as CO2, rather like trees on the terrestrial biosphere do, may benefit from having a larger amount of carbon dioxide in the water. But those which grow hard shells from calcium carbonate will almost definitely suffer as a consequence of this change. So these are areas that we're still trying to work out. So in addition to causing a carbon uptake and acidification, this CO2 addition that we make to the atmosphere is of course warming the planet, causing it to get its climate to warm. That warming is shown at the top left panel here, the warming that's already occurred in the last 100 years or so. And although it's rather small, I hope you can see here, particularly in the North Atlantic, that there are areas which have changed their temperature dramatically less. In fact, they're even cooling relative to global change, whereas the rest of the world is warming. So again, we have this situation of needing to understand the way that the ocean circulates and moves its heat around if we're going to really understand and predict what happens to the ocean in the future. And that top panel is showing you the spatial pattern of change and how that's somewhat complicated. And the lower panel here is showing you that there's also temporal variability. It's not a monotonic increase in warming because of that CO2 rise, although you saw that the CO2 rise is pretty monotonic. The temperature rise on the planet is more complicated, and indeed there's a controversial issue of the last decade or so, really rather small amount of warming. And again, the ocean, because of its high heat content, clearly has an important role to play in that temporal evolution. So I've run through some of the things that are on this rather long list already. We're not going to deal in the next 45 minutes at all with the carbon dioxide any further. We're going to be thinking about the implications of the warming, so that middle block of implications. David will talk in a minute and focus on the wealth of new data that we've got in oceanography and how that teaches us something about heat transport and about changing circulation. And then I'm going to talk largely about sea level change in my presentation that will follow that. You can see there's some other important aspects of that warming, such as sea ice collapse, ocean stratification, changing nutrient supply, and oxygen contents in the ocean. Some things we're not going to talk about at all are that the ocean also has a really important role in coupling with the atmosphere to control some systems, such as hurricane intensity and frequency, El Nino, changing storm tracks, and we're not going to touch on those at all, even though the ocean plays a role in those. And we're also not going to talk about things that are anthropogenically caused, but perhaps not to do with climate. And fisheries is one thing. That fisheries are controlled somewhat by climate, but the dominant impact on fisheries is that we're taking all the top predators out. And then pollution and coastal nutrients are things that we could carry on doing even if we fix climate change. We're not going to talk about those any further. So I'm going to pass over to David now to talk about some aspects of the warming, and then I'll come and talk about sea level after that. David, over to you.
Okay, thank you, Gideon, and indeed thank you for having the opportunity to come and talk to you today. So these are exciting times to work in oceanography, and especially in physical oceanography, which means the circulation of the oceans. Because since I started as a PhD student in 1989, I've really worked through a revolution in our ability to observe the ocean. I think it's one of the most impressive, actually, achievements in science over the last 25 years. So I'm going to start by telling you just very briefly about that observational revolution. And then I'm going to spend the rest of my time talking about ocean models and what they can and what they can't tell us, and how we can then use the range of different models available to us to extract the maximal information about how climate is likely to change. So when I started out in oceanography, what was done was typically to take a ship out into the ocean So this is still done, I should say, but you'd stop every few kilometers, you would drop a line into the, right down to the sea floor, and you take measurements of temperature, salinity, maybe other variables as a function of depth. And then you would come home, you would work them up and plot them along your section and try and do the best science you could with that data. It's kind of, it's very useful to ask, well, how much data is there? Certainly prior to 1990. So what I'm showing you here is a map that was produced around the time I was starting out as a PhD student. So this is for the Southern Ocean. So I've got, first of all, so this is the inventory of all hydrographic data prior to 1990. So each dot represents one of these lines that's been dropped. These are in the 3 summer months. These are in the 3 winter months. This is at 4 kilometers over the entire year. And I want to make the point that this is throwing all the data together and pretending that the ocean is steady. And, well, you can see there are giant holes, especially in the Pacific in winter. There is virtually no data whatsoever. So when people tell you how the ocean has changed since the 1960s, it's worth bearing in mind sometimes just how little data there is. Now, of course, it depends what you're looking at the sea surface. Things are not quite so bad, and certainly in the Northern Hemisphere, where we have a lot of data from ships, so especially in the Gulf Stream, North Atlantic region, the situation is an awful lot better. But nevertheless, beneath the surface, there is very, very little data looking back in time. And here's the number of stations as a function of time. So you can see the Second World War, no data at all. But we're talking about a few thousand stations a year, typically, up until about 1990. Now, things did improve in the 1990s, thanks to the World Ocean Circulation Experiment, where there was a systematic attempt to record the state of the oceans over 1 decade through a global network of ship sections. But it's really since 1992 that the situation has been dramatically changed. The first reason was the advent of satellite altimetry. So this is a truly stunning technology that basically measures the height of the sea surface, if you like, every 10 days with a horizontal resolution of about 150 kilometers to an accuracy of a few centimeters, which I find technically a remarkable achievement. And you can go onto the web, as I did today, and download the latest data. So this is a 10-day window. You can see the satellite tracks here up until today. And what you're looking at is sea surface height anomalies. So the scale goes from -20 to +20 centimeters. And essentially because the height of the sea surface tells you about the weight of the fluid column, it tells you about the pressure in the upper ocean. And just like you use pressure to infer the atmospheric circulation, you can also deduce that the circulation anomalies are then directed around these patterns of high and low sea surface height in the ocean. And then in addition, over the past 10 years, we've also had an equally exciting technology that's emerged known as the Argo float. So this is a profiling float. And as of today, there are 3,800 of these floats out in the ocean. So again, this is a heroic effort. These things are continually being lost. They run out of battery, they get grounded. And it's through the work of very many groups writing grant proposals to throw in another 30 floats that we managed to maintain this network. But nevertheless, this is what we have there today. So these floats, every 10 days, they descend down to 2 kilometers. They drift around for 9 days, so you get the mean velocity at 2 kilometers depth over 9 days. They come up to the surface, and the really clever part is they measure temperature and salinity as they come up. And from that, you can use fluid dynamics to infer how the circulation also changes with depth. So you get both the heat content, if you like, the salt content, and you get the circulation over the upper 2 kilometers on a near global basis. And again, this is today's data. You can download this. Go to the Argo website and download this data. There are some very exciting technologies on the horizon. So gliders is very much with us today, but ramping this up into a global network, rather like Argo, is really the challenge for the future. These are very much like Argo floats, except you can tell them where to go. So you can navigate them from your laptop, if you like, in the back of this room. If you have a glider out there, then you can tell it where to go, and it can take sections across the ocean, or it can act as a virtual mooring. So this is an existing technology, but deep gliders, I think, are very much going to be the future. And then there are always new ideas out there, and one of the more exciting ideas in recent years has been to put sensors on marine mammals. So this was originally done for biological reasons, to track where these elephant seals in the Southern Ocean would go. But actually, now we also measure temperature and salinity as a function of depth. And in orange, you can see all the elephant seal data that's being collected under this program. And what's remarkable is these elephant seals go down to great depths, many hundreds of meters. They even do repeat sections. It turns out, this wasn't known, that they go along the same line. They repeat it all the time, every year. And the elephant seal data really picks up where the Argo data starts to drop off. They go under sea ice, for example. So this is very, very exciting. So once we have all this data, then of course we can throw it together and we can start to answer questions like, how are the oceans warming? How have they warmed? So these, the data I'm going to show you go back before these most recent observational technologies, but here's the observed warming over the upper 700 meters from 1971 to 2010. And perhaps I'll just make the point that the warming is not uniform. As Gideon's already said, ocean circulation plays a big role here. So you can see, for example, enhanced warming in the North Atlantic. And then here is the temperature anomaly as a function of depth. And you can see that the warming is enhanced at the surface, as you might expect, but there is significant warming at much deeper levels too. If we look globally, so here are various different estimates of the observed warming going from the 1950s. So bearing in mind what I've already told you about the uncertainty as we go further back in time, reflected by the larger error bars in some of these earlier estimates. But you can see as we move into the modern instrumental period, the error bars start to decrease, and in fact the independent measurements start to converge. So there's no question that the oceans are warming, and to a great extent. And moreover, the warming is not just over the upper ocean. So here's the upper ocean, the upper 700 meters, but there's almost as much warming then down to 2 kilometers. And the most recent data here also includes the ocean below 2 kilometers too. Contribution here. Okay, so that's all I'm going to say for now about observations. I thought I should say a bit about models. So I'm going to start with some quotes, actually, which I like. The first, I think, is very important, which is essentially all models are wrong, but some are useful, which I think is always worth bearing in mind. So a model is only useful if it teaches you something you didn't know before you started. And getting the right type of model to address the question at hand is one of the important skills in this field. Now, my view is there are 2 types of models that we need to use in this subject. The first are simple models. So this is what I spend an awful lot of my time doing. And I want to give you a second quote here due to Samuel Carlin, which is the purpose of models is not to fit the data, but to sharpen the questions. Now, I think I mostly agree with this. I agree with this certainly for simple models. That's absolutely what simple models are about. It's not about getting the right answer. It's working out what the right questions are to then ask of your more complete models. But where I disagree with this quote is it is sometimes useful to try and fit the data and indeed make predictions as well. And for that, we need state-of-the-art climate models. So I like this quote of Paul Anderson: "I've yet to see any problem, however complicated, which when looked at in the right way did not become still more complicated." And this is very much where IPCC is. Every report, we add yet more complexity to the models. But you really need the simple models in tandem in order to understand what these complex models are able to do and indeed not do, and then draw the right conclusions and indeed ask the right questions. So I thought I would illustrate this with some examples. And the first, this is the most technical part of my talk, but I want to give you a flavor of the work we did under the funding of the Martin School with Law Sanner, who was a then James Martin Research Fellow in the Ocean Institute. And one of the things we did was to develop a new conceptual model of ocean heat uptake. So this is very much a simple model. It's not about getting the right answer. It's about trying to understand which processes might be most worth focusing on in a complicated model. So one of my favorite conceptual models is due to Ganadesican. It models the ocean as two layers, buoyant, or if you like, warm, and cold and dense. And it simply asks the question, which processes deepen the interface between the warm and the cold layers? So you can see very easily a connection with heat content. And it turns out, for reasons I don't want to go into today, that sudden ocean winds push water northwards, so deepen the stratification, they increase heat content. Also, vertical mixing will mix heat down from the surface, so will increase the heat content. And then there's a process, instability or eddies, if you like, in the Southern Ocean that move water in the other direction. So shallow, remove heat content, reduce the heat content in the, and also sinking or North Atlantic deep water formation in the North Atlantic will also act to decrease the depth of this surface layer, so reduce the heat content. And then what we want to do is try and use some plausible scenarios for what might happen. Now, my personal view is it's very hard to predict how some of these forcing functions will change. This is an example of what the models don't do so well. So here is the latest IPCC estimate under the higher emission scenarios for how the overturning circulation or the deep water formation in the North Atlantic is going to change into the future. And all the models show some sort of decline, but there's a lot of disagreement over the extent of the decline, and indeed even the starting value for the strength of the circulation. So really all we can do faced with this is play with different scenarios to give an idea of what the range of possibilities is. Likewise, for Southern Ocean winds, there's been, I think there's a consensus, the Southern Ocean winds are likely to strengthen and move polewards. So what do those do to ocean heat uptake? And then finally, the big caveat is none of our ocean models used for climate resolve these very small turbulent features, the animals of weather systems in the ocean. And so we've done a lot of work on this, so we want to put in some scenarios for how eddies might change the story. So what we do is not solve the two-layer problem, but it's the same idea, but with 100 layers. That's all I was going to say. So effectively, we solve for the vertical stratification of the oceans. And I'm just going to show you some headline results. So the first one, scenario one, is if the ocean behaves essentially passively, if it just diffuses and advects with the circulation, the heat down from the surface into the ocean interior. What we do is we warm the surface by 4 degrees over 200 years, and here is the net heat uptake in watts per meter squared, and we've also broken it down into different depth ranges. So initially at the surface, but as time progresses, we take an increasing amount of heat into the deeper levels. And the crucial point is that the dominant mechanisms, contrary to what some of the textbooks might have you believe, are circulation features in the ocean. So the circulations associated with the Southern Ocean winds and associated with the North Atlantic deep water formation and associated with the Southern Ocean eddies. So it's circulation that's determining the heat uptake in this simple model. What happens if those circulation features change? So let's do some plausible climate, think about some plausible climate scenarios. So suppose our winds strengthen by 10% over the next 200 years. So what happens if the winds increase by 10% is you increase the amount of heat taken up by your ocean. So here's our control I just showed you about. In this case, you increase the heat uptake by about 50% or so. So this is telling you that ocean circulation can have a big effect on the rates of global warming, a big feedback onto the atmosphere. And likewise, if we reduce North Atlantic deep water formation, so here we've done two scenarios where we collapse the circulation by 50 and 100%. We also tried warming the deep water by 2 degrees. That does very little. Well, then we really go off the scale. So the heat uptake then is massively increased in these scenarios. And in fact, most of the heat is then taken up in much deeper levels than in our control experiments at a kilometer or so. So what this is telling us is that ocean circulation has a big role to play in ocean heat uptake. Now, how does this help us understand what we've been seeing recently, the so-called hiatus? So this is the figure that Gideon showed earlier. So the rise in surface air temperatures up until the present day, and the so-called hiatus over the last decade or so. The first point I want to make is that the coupled ocean-atmosphere climate models do show frequently periods where surface temperatures do not increase or indeed even decline, and this is expected. In fact, you can deduce it's likely to be there from our idealized, our simple model. To the extent that the ocean circulation fluctuates in time, there will be periods where heat uptake is enhanced or decreased. So this is a set of 5 climate model experiments. The different colors are the different experiments, all under the same climate forcing scenario, and the black is the ensemble mean. But if you focus in on different periods, you can see regions here in the heavy blue where there's a decade of cooling in 2 of the experiments. Now, why is this? Well, it's essentially because, as Gideon said, the oceans store vast amounts of heat. The upper 2.5 meters of the ocean has the same heat capacity as the entire atmosphere. So if the ocean does anything interesting, then it can have a dramatic effect. Just to emphasize this point, this is going back to data now, sea surface temperature anomalies from 1930 to 1960 minus the following 30 years, from 61 to 1930. So you can see that the North Atlantic was an awful lot warmer in the earlier 30-year time window compared with the latter. And this is, has become known these days as the Atlantic multi-decadal oscillation, as revealed by taking the North Atlantic sea surface temperatures, detrending them, and doing a running mean, and you see this apparent oscillatory pattern. What I want to stress, it is not an oscillation. This is just a fluctuation. We haven't got enough data to infer an oscillation here. So this is almost certainly just a fluctuation in sea surface temperatures. But nevertheless, the sea surface temperatures in the Atlantic do fluctuate by a significant amount. And this is associated with changes in the overturning circulation in the North Atlantic. And then there have been a number of different papers that have tried to understand what's caused the hiatus over the last 10 years. And one of my favorites that was recently published was by Sieben Dreifout and co-authors at Southampton. This shows you the sea surface temperature change from the last decade compared with the previous decade. And you can see indeed enhanced warming in the high latitude North Atlantic, but also in other parts of the ocean. And they tried to summarize what they found in this cartoon, and basically it's all of the same processes that Laura and I were finding including in our simple model that are contributing to this, along with the tropical Pacific. So a range of different ocean dynamical processes conspiring over this past decade to give us the increased ocean heat uptake, and hence the so-called hiatus. So there really is no basis, I think, for arguing that global warming has stopped over the last decade. It hasn't stopped in the ocean. But certainly the atmosphere doesn't control much heat. So if you were to think of the atmosphere as perhaps an iPod, the ocean is like a sound system in a stadium, and the atmosphere has to dance to the ocean's music on these timescales, and that's all that we've been seeing. Now I want to end, before Gideon throws me off the stage, by asking a related question, which is how reliable are projections of some of the key ocean indices, such as the Atlantic overturning? And this is an example where the models really do less well. So I've already talked about this figure. We have observations these days that tell us that the strength of the circulation is about 17.5 spheredrops in the present day. So the models are out in the prior to the present day. And then there's really no consensus on the extent of the reduction in overturning over the next century and beyond. Now, of course, if this circulation weakens, what it does is transports less heat to high latitudes, and this is believed that this is why, well, it's known that this is why we see much less warming over the North Atlantic. In these climate projections, the overturning circulation is weakening, and therefore we take less heat northwards, and that counteracts the effect of global warming just in the North Atlantic sector, which is why you see even a slight cooling in the figure Gideon showed earlier. Now, what is the problem here? Well, the problem is that the ocean models fail to resolve many of the critical processes you need to capture in order to answer this kind of question. So the sinking occurs in narrow plumes of maybe a kilometre width. That dense water that's formed perhaps in the Norwegian and Greenland seas then has to overflow into the Atlantic with a lot of entrainment. Again, you need to get down to scales of a few kilometres. There's a beautiful paper by a postdoc here, Renske Gelderus, from a PhD, showing that Labrador sea eddies with scales of a few kilometres are critical for determining the properties, the water mass properties of the water in the Labrador Sea, which again is an important driver of overturning. And then the Gulf Stream itself has a width of 50 kilometres. And when you think that our climate models currently have a grid spacing of 1 degree, maybe 100 kilometres, you can see that there is an issue here in trying to capture these features in the state-of-the-art models. So that's giving you a negative perspective. But despite that, there are things we can do with these models. It very much depends which question you're asking. That's what I want to stress now. Let me just go back briefly to the observations. So what do the observations tell us the overturning has been doing? Well, prior to 2004, we didn't know, is the answer. But thanks to a program that was led by the UK, so I was not involved in taking these observations, I should stress. It's led by the Southampton group, but with partners in the US also. Over the last 10 years, we've been making measurements of or estimates of the overturning circulation at 26 North in the North Atlantic, and here is the time series. So you can see again that it dances around like crazy on all timescales that you can see, and over this 10-year window, there has actually been a very slight reduction, which is not necessarily due to anthropogenic forcing. This just could be the ocean fluctuating as it does on decadal timescales. So that's what we observe. So let me show you a result we obtained recently just to give you an idea that the current models can make some very, very useful, skillful predictions. So for small anomalies, you can try and reconstruct what's happened over the last 10 years to this overturning by using the model to calculate what the sensitivity of the overturning is to surface fluxes of momentum, heat, and freshwater, so the wind forcing, the heat flux, etc. And then project those onto the surface fluxes. So this is a mathematical equation, complicated mathematical equation that I've shown you here as pictures. If we multiply the model sensitivities against the surface fluxes, this is what we get, and the colors show you how far back we've gone in time in accounting for surface fluxes. So the ocean has memory of fluxes going back into the past, and it turns out this methodology works up to about 15 years, beyond which it starts to break down. So the red line, if you like, is our best model prediction. The black line is the observations at 26 North, and I find it remarkable that we recover much of what's been observed over the last 10 years. Although if you look more carefully, we do very well on the annual timescale, the interannual perhaps timescale. That's because this is dominated by wind forcing. What we do less well on is the decadal timescale, which we believe is dominated by high latitude buoyancy forcing, high latitude cooling. And it's very exciting for me, this result, because one of the new projects we're involved with is an attempt to monitor the circulation in the subpolar North Atlantic in a program called OSNAP. And it's going to be addressing the question of what happens at high latitudes. It's precisely the processes where I'd argue that the models do less well at present. So I hope I've given you some flavor of why these are exciting times in oceanography, because we've got new observations that for the first time give us in unprecedented detail a picture of how the ocean is changing, at least over the upper 2 kilometers. And it's an exciting time because we've now got modeling tools that really can start to tackle many of the most pressing questions, but there is an awful lot of work left to do that will certainly keep me busy for the rest of my career, indeed my students busy for the next 40 years. So I'm going to hand back to Gideon now.
I don't quite know why we're changing computers now, but we are. Thanks. So I'm going to switch gears a little bit and talk about sea level now and sea level change in the future. And to start with, I'm not going to be saying a great deal that connects to David's talk, but I think you'll see as I go through my comments that there are serious connections between our ability to understand and predict sea level and hopefully we get something on the screen. It worked before. as we said before, it always works when you test it and then it doesn't work in the actual performance. No, that was just the power. Oh, does it? Oh, there you go. Oh, maybe that did make a difference. Thank you. Cheers. So let me start with another lovely satellite image, and this time we're looking at a view of Greenland with the clouds taken away. This picture shows you about 6 meters worth of sea level. So if you took that ice off Greenland and dumped it into the water, you get about 6 meters of increase of global sea level. So is that likely to happen? Well, we can get a clue about that if we look into the past. I can take you back 130,000 years into the past. This is a period that we often look at as an analogue of a slightly warmer than today world, perhaps the last time the world was slightly warmer than today. Using a variety of different chemical proxies, we can look at temperature here around the Arctic Ocean and see that temperature rise at 130,000 years ago was about 2 to 4 degrees. A temperature rise that we expect to get at these polar latitudes really quite soon in the future. And this is a model result showing you that about half of the Greenland ice sheet was expected to have melted at that time. So a significant amount of that ice, therefore, in the ocean. Now this melting of Greenland and indeed melting in the other hemisphere is indeed witnessed, and we can see clear evidence for sea level change, levels much higher than today if we look into the past. Here's a lovely example from the coast of Oman. You can see the sea level, you can see the tidal range, relatively small, and this perched up here on top of this platform is a coral reef from 130,000 years ago. And this shows you that sea level was up here, something like 6 meters above modern at 130,000 years ago. So clearly we can melt significant portions of Greenland at temperature change, not that much more than we see already, and that we expect in the near future. 6 meters of rise, which is what we see globally for the last interglacial, will be enough to do this to New Jersey and New York. The blue colors on here showing you areas that will be flooded by a 6 meter sea level rise. So you lose much of New Jersey. Those people who have been to New Jersey, you may see that as a positive feature of climate change. But I think what you get a sense of pretty quickly here is that this sort of level of sea level change is very significant. And regardless of whether we get this much change, this is an example where sea level is quite, the coast is quite sensitive to sea level change. This is the sort of thing that has happened to New York. Well, no, not quite. This is a still from a movie, of course, but it's not so very different, in fact, from what has happened to New York. This is the New Jersey coastline during Hurricane Sandy not so long ago, and another picture of it shown here. So these are examples, actually not quite sea level change, because this was a storm surge, both in the movie and in real life, rather than global sea level change. But it demonstrates how this is a vulnerable area of the coastline. And of course, storm surges like this, if you change the sea level and take the whole base level of sea level up, storm surges become even more significant and cause even more damage. So we are going to see this sort of sea level. We know that temperatures are going to get higher. We know that sea level is going to go up, and we're going to have to deal with that. And I see this as one of the really unstoppable features of climate change, with possibly some of the most serious implications about climate change. That sea level change is pretty much locked in already, and we can control the amount of it, perhaps, but we need to understand it much better. And that's what some of the work that we do here in Oxford, and it ties back to some of the work that David is doing and talked about earlier. So what has happened to sea level so far, to global sea level? There's 3 different timescales here showing you that for the last 3,000 years, sea level has been relatively stable here. That is the meter scale here. And then blow-ups of more recent periods here, showing you that sometime in the 1900s we started to see an increase of sea level. And we now have very good data from satellites and tide gauges that show us for the last century what's been happening to sea level. And it's been going up at about 3 millimeters a year in the last decade or so. So we've got a pretty steady increase today, and it's led to about 190 millimeters, so about that much sea level rise during the 20th century. So we've got this steady increase of sea level that's going on today. What about the future? Well, first of all, I want to show you a picture from AR4, so not from the most recent IPCC, but from the version before that. And this is what they projected for the future. They showed the same sort of data that I've just shown you here, and then they projected off into the future to suggest about 350 millimeters by the end of this century, so about 1 ruler worth of sea level change by the end of the century. But at the time of that AR, they made a very, they caveated their view very explicitly. They said, further accelerations in ice flow of the kind recently observed in some outlet glaciers substantially increase the contribution from the ice sheets. Understanding of these effects is too limited to assess their likelihood or to give a best estimate. So that number they gave of 350 millimeters was a lower estimate, and they said there could be a lot more, we're not able to work it out just yet. And that was because processes such as this moulin that you see here are very small scale, very difficult to model, and a lot of the important stuff is going on 2 kilometers below the ice sheet where you can't easily sample it. So one of the big challenges that we've been trying to face up to in between the assessment reports is to try and improve our understanding of how quickly the ice sheets melt. We know that they do. Here are 3 slides that show you the meltback of a Greenland outlet glacier in 3 different years. Here, the sort of rough stuff on the right here is melted ice sitting on top of a lake, and the striated stuff is the glacier itself. And you can see the lake clearly getting bigger in these images as the glacier melts back with time. And there are many other examples of this sort of behavior. That's going on all around Antarctica as well as Greenland. This is a very recent compilation using satellite data. These circles on here representing the data for each of these areas, showing that the whole of Antarctica is busy melting and the glaciers are flowing off into the ocean. This is based on observations of the surface of the glaciers. We also have this wonderful technique called GRACE, which directly measures the gravity field of the planet and is able to tell us the mass of the ice sheets and how they've changed through time. These are amazingly clever satellites. They fly about 220 kilometers apart around the Earth, and they're able to measure the distance between them to an accuracy of 10 microns. And they're able to, as they go across anything massive below them, like an ice sheet, they get pulled apart or pulled together a little bit by changes of gravity. And those very small changes in distance, therefore, enable you to reconstruct the gravity field underneath the satellite. And we can use them to do all sorts of things, including work out how the ice is melting. And here you see 2 images in different years showing you that Greenland is growing a bit in the middle, but losing mass around the edges. And that's an accelerating process in these 2 images. So Greenland is falling apart with time. So that sort of data from satellites and from tide gauges and such like has been used to refine the estimates from AR4. This is now the AR5 IPCC assessment of sea level rise. But you can see it hasn't gone up that much, actually, despite the fact we've got evidence for these ice sheets collapsing. If we keep a low emission scenario, the increase is really not that much more than we saw at AR4. And even the very high emission scenario here, we're only getting up to something like 70 or 80 centimeters, so still less than a meter. Now, IPCC is sometimes criticised for being overly scaremongery and sort of trying to make climate change sound as if it's worse than it really is. But I think this is an example where it's the other way around. I think that this is an example where it's too conservative, and the truth in the future might turn out to be rather worse than this, and a rather larger sea level change. And there's a few areas of evidence for that. If we take the most recent assessments from that GRACE satellite of what's happening to our ice sheets, you can see significant melting in Greenland and indeed in Antarctica here. And we've now got long enough time series that we can plot what's happening to these ice sheets through time and see what's happening in what the rate of change is. So this example from Greenland, just look at the blue data, which is the GRACE data on here. We now have a very good understanding of how quickly the ice is melting, 280 gigatons per year, but also the fact that it's accelerating, and we get actually a rate of change of that ice melt. So we can project a rate of change into the future and say that really sea level change is expected to accelerate, which isn't really incorporated into the IPCC AR5 estimates. Another example, which is one that we've worked on very directly here in Oxford, is to again look back into the past. I did that with a 130,000 year example at the beginning of this sea level section. And we can also look back into times when sea level was changing rapidly in the past and see how quickly can you change sea level. This is a reconstruction of sea level based on corals for the last 20,000 years here, showing you that during the height of the last ice age, sea level was much lower, 120 meters or so lower than today. And as it's melted up towards the pre-industrial value on here, there are some quite big steps, particularly this one here, which is called Meltwater Pulse 1A. And we've worked on this in some detail. I'm not going to talk through this graph in detail, but you can see this meltwater pulse in many different records that we've looked at. And this pulse is about 17 meters of sea level rise, occurring in about 350 years. So it's a very rapid change of sea level. It's about 15 times faster than what we see today. Now, the world was very different back then during deglaciation, so this is not a direct analogy for what we'll see in the future, but it demonstrates the ability of ice sheets to collapse very rapidly and add to sea level very rapidly in some conditions. There's also some evidence that we might be about to see that sort of behavior again in West Antarctica. West Antarctica is unusual, or is different from East Antarctica, because the base of the ice sheet there is effectively underwater. And you can see in this cross-section that goes across Antarctica here, if you look at the left-hand side here, which is shown over here, and you see sea level, the blue line gives you an idea of that, you can see that the ground is basically underwater. And this means that if you start to melt back, if the ocean warms the ice, as it's doing, and we saw in some of David's data, as that ocean warms the ice, if you retreat back into the area where you're deepening with more melting, then you get an acceleration of ice meltback, and you see a much more rapid meltback and a potential collapse of the West Antarctic ice sheet. Now, there's evidence as of last year that just that collapse might be happening. This is some data, the same sort of satellite data that we looked at before, showing very rapid flow of some of these ice, some of these glaciers into the ocean in West Antarctica in this little region here. And using this data coupled to some models to constrain those models better, this predicts that we're already in the early stages of a collapse and that may accelerate into the future. So we could easily expect to see faster ice collapse than we've seen up to now in future times. Now, there are a number of people who, even at the time of AR5, were saying, well, we don't think that projecting from current trends into the future is necessarily the right way to get sea level. And they looked at several different ways of trying to analyze possible sea level change using paleo data from the instrumental record and from older timescales. And they come up with these things that are called semi-empirical sea level predictions. They're using data, they're looking at empirical data, but they're not really trying to understand the physics. They're just saying, let's look at the patterns that we see and use those patterns to project something about the future. So this is a figure that's taken from the IPCC, but it's not their headline image. And it shows you what we might expect for different emission scenarios using these semi-empirical models. And you can see there's quite a lot of scatter in each one of these, but you can see that in each case, the models are typically suggesting something which is greater than the physical models. So the physical models which are used for the headline numbers are the grey bars on each of here, showing sea level rise by the end of the century. These semi-empirical models that try and capture something about unknown processes in the physical models are all suggesting greater sea level rise. And with emission scenarios that are relatively large, such as these ones, we're seeing sea level rise that in many of these models goes beyond 1 meter by the end of this century. I've also, although I haven't put a figure of it here, I've also mentioned expert elicitation here. So there's a study a couple of years ago which looked up, just asked a bunch of sea level people and ice sheet people and said, well, how much do you think sea level is going to go up by the end of the century? And very many of those experts said 1 meter is a really plausible number. So those IPCC numbers that suggest 70 or 80 as the worst case, 70 or 80 centimeters as the worst case scenario, may well be too cautious, and we might expect to see sea level of 1 meter or more by the end of the century. So what does 1 meter of sea level look like? Well, it's a pretty good rule of thumb that 1 meter up is 100 meters in. Now, of course, it depends where you are. If you've got a cliff, you don't go up, you don't go in at all. But if you've got a low-lying marsh, you're going a long way. So that's kind of an average number. And you can see what it looks like on this image. This is a somewhat simplistic image. It's just assuming sea level goes up everywhere by 1 meter and that you don't have any flood defenses. But this is what would happen if you did that. And you can see significant inundation of parts of Europe as a consequence of that sort of sea level rise. So this would clearly have significant societal impacts. You could look at close-ups of London. Indeed, you can get websites that do this for you and show you what happens to something like London with a 1 meter sea level rise. But an important thing to caveat that with, although 1 meter is an important rise, even if it's global, is that the global sea level rise is not what we expect. We don't expect to see this sort of behavior in our sea level rise with tilting sea level quite that abrupt. But we do expect to see non-uniform effects. We're not going to see sea level just go up by 1 meter everywhere by the end of the century. And the things that control that are several-fold, and I've listed the major ones here. One is that ocean temperature change is not uniform, as we saw clearly in David's talk. Circulation change also plays a role. Again, we saw some of that information in David's talk. Atmospheric pressure, which is a very minor effect, can cause sea level changes, and then ice sheet gravity and isostatic processes. So I'm just going to quickly run through each one of those in turn, except for pressure. So ocean temperature, first of all. This is where you start to see the value of those rich observational data sets that we've had in recent decades in terms of our ability to understand the spatial pattern of sea level change. And you can see here that the sea surface height change, that's effectively telling you what's happened to the sea level, but with a regional pattern. And this is that sort of satellite data that David showed you with the sort of crisscrossing lines that made a nice coloured mosaic on the board. And you can see that we know in some detail what's happened to sea surface height. And this is showing you the sort of data we get from those Argo floats, which show you what's happening to salinity and temperature with time as well, and enabling you to work out how much of the sea level change that we see spatially is being caused by temperature and salinity changes spatially, causing density changes. So these density changes imposed by temperature and salinity are driving the local regional distribution of sea level. So that's an example of how we might expect to see changes because of differential heating. How about circulation change? Well, as David showed you again with some of those sea surface height images, the ocean is not completely flat. It's not as sloping as you saw in my slide a couple of images ago, but there's a couple of meters of topography on top of the ocean, which reflects the fact that the ocean is dynamic and that it's moving around. So this dynamic topography is built by the wind, and it drives the ocean circulation. So where there's significant currents here, you can see the most significant topography. So for instance, the Gulf Stream flowing through here, you can see significant topography with a low around Greenland and a high down here towards the Caribbean. And similarly, large sort of topography in the surface in the southern hemisphere where there are very strong current systems as well. So you can see, I think, from this image, what would happen if you were to dramatically change circulation is you'd change this pattern of sea surface height regionally. And we can work that out in models. You can say, well, the models that David was showing you that predict what will happen to circulation in the future, what do they predict for sea level change in the future? And this is an image from IPCC which combines together the temperature effects and also the circulation change effects. And you can see there are big changes globally, but perhaps most particularly along the eastern seaboard of the USA, where circulation changes and temperature changes are imposed on top of each other to lead to quite substantial additional changes. So if you live up here somewhere in Newfoundland, you're going to get your meter of global sea level, and you're going to get 30 centimetres more, potentially, because of these regional effects as well. Other regions, of course, will do rather better. So I've skipped out pressure, which is a very small effect. So let's move on to gravity next. And ice has mass, as we saw with the GRACE experiment. So if you take some of that ice and you dump it into the ocean, there's less mass in that part of the world, and therefore the ocean is no longer drawn towards the ice sheet quite so much. So this is an image that shows what is expected already to have happened because of loss of mass on the two hemispheres. So as you lose some of the ice on Greenland, the water effectively is no longer drawn towards Greenland quite so much and flows away a little bit. So you get relative sea level lowering where you're losing ice and preferential water piling up in other regions. So we can see this effect going on today as well as the ice melts. And a fifth area is isostatic compensation, and this is caused by the fact that when you load something like ice onto the surface of the Earth is, at some time scales, actually behaves like a very slowly moving liquid, and it's pushed down by that load on top of it. When you take the load back off again by melting the ice, the Earth very gradually recovers and bounces back up again. And somewhere else, if one bit's bouncing up, somewhere else must be gradually subsiding to compensate. So you get these complex patterns in the solid Earth as a consequence of changing the loading on the surface. And here's a nice example from the UK, where you can see that most of this is just looking at that isostatic effect, and you can see that most of the UK is actually going down a little bit, so just sort of gradually subsiding, and that's because of this sort of the far field effects of taking off ice sheets in Scandinavia, that Britain is slightly sinking. But also we had an ice sheet on top of Scotland, and the fact that that's now no longer there means that Scotland's bobbing up a little bit, and it's being uplifted here. So you get very strong regional patterns because of this isostatic effect. So if you want to understand the regional pattern, you've got to understand those gravity effects and those isostatic effects as well. And both of those effects are captured in this IPCC image, which again combines those two to show what we expect by 2100. And again, quite pronounced changes, particularly around the Northern Hemisphere region where ice is changing and ice changed in the past, and we're still recovering from it now. So you can see, I think, quite clearly that not only do we have concern about the fact that the sea level is going up, but there's also a very significant range of effects which cause local changes, some of which can be quite large, and pointed out the scale on here, but you're seeing changes that are up to another metre here. So as well as the global change of a metre, you might see regionally an additional metre of change. So my sort of concluding slide here is this one. We know that sea level will keep going up. I think that's pretty much a fact about climate change. It's one of the things I really hang my hat on. We know it's getting warmer, we know it's getting warmer because of CO2, and we know sea level's going to go up. Those are three things that we're really very confident about. We know it's going to go up faster than it has up to now because it's getting warmer, and because that warmth is penetrating into the ice sheets. And we also know that it's going to go up at different rates around the world and cause more problems in some places than in others. What should we do about this knowledge? Well, as a scientist, one thing we should do is to continue to try and understand the problem better and to make predictions that are better and to use the wealth of data that David showed and that we're collecting in other programs to improve our predictions. As a society, what we've got to do is break our dependence on fossil fuels. I've said that we're going to melt some of the ice sheets anyway and sea level is going to go up anyway, and that's definitely true, but we can still control how quickly it goes up and the maximum amplitude that it gets to. And as a really sort of something that brings you back home on this one, if you imagine that we heated the Earth enough to melt the East Antarctic ice sheet, the great big block of ice sitting on Antarctica, that's worth about 50 metres worth of sea level. And that isn't going to go in our lifetime or our kids' or our grandchildren's lifetime, but if we lock in enough warming in our century, we'll be leaving that legacy for future generations. So this is an issue that really, if we think about why Paris is important, I think these are one of the issues that we really should be concerned about. And I know that's one of the themes of this lecture series that we're speaking in here. But a third point that I think is very important to make is that we really need to adapt to sea level change. Just saying, okay, it's coming isn't enough, we've got to get ready for it. The changes are slow and we can predict them really already quite well. We can see them coming, we need to plan for them a long way in advance. If you're going to build a city, the typical building stock is about 50 years. That gives us enough time to retreat from coastlines as long as we start doing it now, rather than waiting until the sea level's already up and lapping at our front doors. So here are my closing messages, but rather than finish entirely on a sea level theme, I'm just going to finish with the image that we had at the beginning of the satellite ocean rather than Earth, and open the floor to questions to either David or to me. Thanks.
Sorry, I just lost my concentration. I didn't know whether you were saying a few closing remarks. Now, I know we'll have a lot of questions, and we've got about 25 minutes, so I'll attempt to take as many as possible. So we'll start with the gentleman just there.
Thanks. Hi. So 2 quick questions. In your earlier slide, you were showing that the North Atlantic was warming, and then it was cooling in other slides. I'm not clear what it's doing. And the second question is, you got a lovely picture of the Pacific, which is the largest body of water. You didn't talk too much about what's happening in the Pacific. You concentrated on the North Atlantic quite a bit. So those are the 2 questions, please.
Yes, okay. So the ocean, I probably caused confusion because I showed you 3 different periods of warming. So I think Gideon's slide had a figure for the last 120 years, was it, or so? I showed you then the 1930 to 1960 minus the following 30 years, and I also showed you the change over the most recent decade minus the previous decade. So the Atlantic has warmed over the past decade. It was warmer from 1930 to 1960 relative to the 30 years that followed. Overall, the oceans have been warming. What I was trying to say is the pattern of warming is not uniform. And there are fluctuations on the multi-decadal timescale, especially in the North Atlantic sector.
I think that the reason for focusing on the North Atlantic is that is areas where there are very significant oceanic processes which we know change with time. And if I was to go, in fact, I could maybe if I can get back to my slides at the very beginning here. Yeah, that one. So this image shows you the fact that you've got such intense carbon storage going on in the North Atlantic here is because you've got the initiation of ocean circulation here. This is where water leaves the surface ocean and goes down into the deep ocean. This is an area which is taking carbon for us and taking it into the deep ocean today. And that process of deep water formation is very fundamental to lots of oceanic processes.
Indeed, I forgot to answer the second part of your question, so apologies. Also, I'd add to that in the Southern Ocean, also you can see not quite so much colour, but there is water sinking to great depth over the entire longitude band in the Southern Ocean too, which is why the Southern Ocean is very important and why Laura and I focused on the Southern Ocean too. With the Pacific, I mean, one of the hypotheses that's been put forward for the hiatus is associated with the tropical Pacific and suggestions that it's La Nina conditions. The Dry Falterdale paper found that contributed, but it certainly was not the whole story. There were contributions from Southern Ocean processes and also the high latitude North Atlantic.
That's a good point, actually. We said explicitly at the beginning we weren't going to talk about El Nino, and that's one of the dominant things in the Pacific that you would want to worry about if you were thinking about oceanography.
Yeah, so the tropical Pacific especially is tremendously important. We had 50 minutes, we emphasised the high latitudes here.
Next, one down at the front here.
Thank you. Robert Chris from Open University. I'm interested to know whether or not, or what role you think the oceans could play in the various different technologies that are proposed for geoengineering, for intentional amelioration of climate change, and whether those processes, whilst they might sort out what's going on above the ocean, in the atmosphere, might make things that are going on inside the ocean worse.
Well, you've given, this is perhaps a little bit of a stretch, but you've given me an excuse to show the slide I wanted to show.
He's saying I didn't have room for this.
No, we didn't. We decided not to include this material because it was just going to go on too long, but I'm going to include it now. So probably the most mature technology or idea in terms of trying to get the ocean to take up more carbon is to fertilise it with iron. So we know that iron, the metal, is a very important nutrient in the ocean and indeed controls the amount of life in many places. There's been quite a lot of work done about what happens if you add iron to the ocean and how much additional carbon that might enable you to take up. But of course that's a very risky thing to start playing with, and this is the ocean ecosystem. A lot of people rely on that for food. It provides lots of our oxygen. There's all sorts of reasons why you wouldn't want to tamper with that without really understanding it. And this figure shows you how little we understood it back in 2006, showing these are all the measurements of iron in the deep ocean that had ever been made up to that point. It's a difficult thing to measuring iron in the ocean, because you're trying to measure nanomolar concentrations on a great big rusty ship. So it hasn't been measured very much, but in the recent years, that's changed beyond recognition. And David was talking about physical measurement and how there's been a revolution there. There's also been a revolution in chemical measurements. This rotating image is taken from the Geotraces program that we were heavily involved in here in Oxford. And it shows you all the different cruisers that have measured iron in the Atlantic and reported their data publicly already. So we've got a much better understanding. That was a bit of a stretch getting that in there, but it's a good example of how we're trying to understand the ocean better so that we can then assess some of these geoengineering schemes correctly and really work out what the risks and the potential is of those schemes. Is that enough?
Well,
I think the honest answer is the vast majority of oceanographers would be very, very nervous about undertaking geoengineering. When it comes to talking about some of the changes in the deep circulation, there are great uncertainties. I would be very, very nervous. And also it has to be said, when iron release experiments have been done, yes, we do see increased biological activity, loss of carbon from the upper ocean, but it's transient. Most of that is then recycled back up to the surface. So you'd need to dump a hell of a lot of iron into the ocean. The other one we've looked at is increasing the alkalinity of the oceans, dumping lime into the ocean. I mean, again, my personal view is it doesn't make a lot of sense. The numbers don't really stack up. But
next question, just here. Could you wait for the microphone? Thanks.
Sorry, I'm a complete non-expert. I'm very impressed by the empirical measurements for sea temperature that you showed, and with over 3,800 gauges and so on. Gideon, I was just wondering, you gave very generalized slides. How can we, and how do we have a similar sort of empirical coverage for sea level change measurements? But given isostatic recovery, geotectonics, etc., I can see a lot of complications. So how accurate are the sea level change empirical measurements, and how extensive?
Well, I am going to refer back to slides for that, because I think very is the answer. I mean, I haven't shown as much data in my talk as David did, but a lot of the data is extremely empirical. This is one example here. So these different lines on here, I've forgotten which one's which, but one of those lines is based on tide gauge data. So there's countless places around the world where there are things that measure what's happening to sea level every day. They were established so that people could predict the tides better for fisheries and shipping, but they also measure sea level for you. And then more, so that we've had that data for a long time. And then more recently, we've had the satellites that tell us about the altimetry, so they do directly tell us about sea level. And that was the sort of, so David showed some of that data, and I can repeat this slide again and show that this is a satellite direct observation of how high sea level is. So we really know how high sea level is today and how it's changing with time. I think there is, in the same way that David stressed the revolution in the last decades, I think that's true about sea level data as well. It's starting to, and the other example that I used, if I skip back to the GRACE data, this sort of data, and this GRACE was only flown, this gravity mission was only flown in 2002, I think. So we've only just got enough data to be able to see the acceleration, but we are getting it, and we're getting it. Yeah.
But it is an ongoing challenge on all these programs to keep them going. You know, a lot of the agencies, especially in the US, like to fund a new program that's exciting, and they would say, we've done altimetry now, so, you know, let's do something else that's exciting. And what we need are these key measurements to be extended over many, many decades, ideally with overlapping instruments, of course, because a data gap creates its own problems. We've been lucky so far with the altimetry that we've been able to do that. And the GRACE data, you know, is marvelous. It's not just giving you the information about the oceans and the sea ice. I mean, it's also measuring groundwater as well. You know, how else could you do that?
All forests,
yeah.
Next question, in the middle at the back there.
Thanks. You showed for the sea level rise, you showed mainly the time frame, like for the next century from the IPCC, but you could clearly see that it's like just rising at that time. And even if we stabilize temperature at a certain temperature rise, you would expect to have this long legacy of continuing sea level rise. Is there any estimate how long would it go on if we say stabilize at 2 or 3 degrees in 2100?
I think that the estimates for that are rather poor at the moment. Perhaps you get a sense of that from what I tried to convince you about, that even the IPCC assessments by the end of this century have a fairly large degree of uncertainty. What we expect to happen in the more distant future, I think, is a very active area of research. Some of my own research focuses on paleoclimate, and that's an area where I think that's got a lot to teach us, because then we can look at what does the mean state look like in the world, and with different amounts of global warming. But I would be fairly confident in saying that we can expect to see sea level rise continuing for some centuries. Exactly how high sea level gets to in the end is dependent on what we do this century, and we have a very long repercussions of our behaviour this century. So it could go on for thousands of years.
Yeah, this I'm going to give an answer to. It's not an answer to the full question, but a part of it. But one of the things we've been doing with our simple models is to try and address that question of what's the adjustment timescale for the global ocean stratification, and sea level indeed. And the answer is certainly centuries, probably order 1,000 years or so, which you can understand in terms of relatively simple physics. So there's some uncertainty on there, but certainly sea level I would expect to go on rising for some time.
More questions. I'll come back and let you have another one, but is there somebody? I thought I saw a hand over here. No, okay, we'll go back to you. Sorry.
All right. So simple model scenario, right? you've got the planet warming, it melts the ice gets dumped into the oceans, which cools the oceans. Doesn't one effect sort of neutralize the other?
Do you want to do that one?
Oh God, this is I mean, look, if you go on to very long timescales, there are lots of feedbacks, and they're often misunderstood in a global warming context. They're often seized upon by the skeptics to use to counter the arguments that the global warming is man-made. Just to give you one example, these are issues that we're trying to address at the moment by trying to understand glacial interglacial cycles. So one of the embarrassments, I think, in the field is we actually cannot explain the large magnitude of the fluctuations we see between glacial and interglacial periods. A lot of people believe that the ocean acts as an amplifier of the relatively small changes in radiative forcing associated with orbital variations. If you change the ocean circulation, the stratification, you can outgas huge amounts of CO2. The oceans store 50 times more carbon than the atmosphere. So small changes in circulation can have a big impact on atmospheric CO2. The natural response of the oceans to warming is actually to outgas CO2, to act as a positive feedback. And that's the point that often gets missed. So if anything, I think the risk is on the upside rather than the downside. But, you know, these are...
Well, I actually think that I agree with everything David said, but I think that your question is also not quite right in the fact that if you've taken ice that was sub-zero and you've melted it, you haven't made anything cooler, you've actually made it warmer. So the total amount of heat in the Earth has gone up, and you have to overcome the latent heat of fusion to melt the ice. So some of the energy has gone into doing that, but ultimately what you're doing is adding to the warming, and I think that's part of the warming trend that we're experiencing.
More questions? There's one here.
Yesterday, Miles Allen was talking about Paris, and the missing part from the agenda was CCS. That's an aside. But he had some recommendation that when global temperatures reached 2 degrees above, that everybody should either must capture all their carbon. And I put it to him because I thought there was a time lag, that you can't stop it at 2, because then it would continue. And he said, no, that's not right. And he blamed the oceans. He said somebody called Solon or Ceylon has said, no, the ocean will then mediate. The ocean will continue to absorb CO2, but then emit temperature. And that will balance it, so you can stop it at 2 degrees C rising. Is that something?
I think what Miles is saying, Miles and his group is saying, is that the dominant effect seems to be it's the total amount of carbon emitted that determines where you go to on long timescales. Now, the ocean will take centuries to catch up with the forcing, but I think what he's saying is we're perhaps a little too obsessed with the rate of emission, and the more important quantity is the total amount of carbon that's emitted. I mean, from the ocean point of view, it doesn't make a lot of difference, you know, on the 500-year timescale, whether it's done this decade or the next. The long timescale response is going to be relatively similar, I would argue.
But if you really could put the handbrake on completely and just stop CO2 going up, things would get better because the ocean continues to circulate, and you saw that picture before where some carbon is going down into the deep ocean. That continues to happen. Yeah. So carbon would continue to be removed from the atmosphere, slowly, but it would happen. And indeed, the heat that's in the ocean would continue to spread out. So we would, in fact, and if you put this into a full model, you do see that it actually continues to warm just for a little while, and then you see a gradual decrease below the peak. So I think Miles is correct. The challenge, though, is how the hell do you stop everyone from burning fossil fuels just like that? You can't do it, right? So you have to start now.
And not back to where we started.
Yeah, but you should, and indeed, how do you suddenly do CCS just like that? So we have to start doing that.
Any more questions? I've actually, yeah, here.
Slightly oblique question for Gideon, and I hope he won't mind me asking it, but you've said very emphatically how important it is to cut carbon emissions straight away using fossil fuels straight away. And yet I know your department has very close associations with Shell. I'm sure you have rational explanation and good reasons for that. You may, for example, use that connection to exert influence on what Shell does. But I'm just interested in your reconciliation of what you said on the screen and what your department does. Hope you don't mind me asking.
No, that's a good question. Thanks for putting me on the spot. Well, it's a personal challenge for me. I'm a climate scientist, that's what I study for my day job, but I'm also running a department, and geology departments have a long heritage of looking for resources, not just oil and gas, but mineral resources as well. So there is a tension there, and I think it's a tension that earth science departments find themselves right at the centre of. The most fundamental answer to your question is that as a group of scientists, two components to this. As a group of scientists in the department, there has to be academic freedom, so people can choose to research what they want. Not completely, but pretty much what they want. And secondly, that all departments are facing up to societal challenges, and there are different societal challenges. I think one of the most important ones of today is about climate change, but there is also the challenge of how do we keep the lights on? And at the moment, we're relying on fossil fuels to do that, to keep the lights on. And if we suddenly stop burning fossil fuels completely now, we couldn't keep the lights on. So there are certainly people in the department who have the ability to choose what they research, who are choosing to research energy security by helping oil companies. So I guess that's a more philosophical answer. In the actual explicit case that we do get a lot of money from Shell, a large chunk of that money is to understand the carbon cycle. And the carbon cycle is a very interconnected beast, because the carbon that we're putting out into the atmosphere now was locked up at some time ago in the past. If you want to understand how the carbon cycle operates, you do need to understand where the resources are and how they were made. So it's actually quite interesting to understand oceanognoxic events with money from Shell, especially when money from the government is declining. And I'm struggling to understand them, and the department is, as a climate problem, but it has implications for Shell as a resource problem as well. It's a good question.
Any more questions before I selfishly ask my own? Yes.
I read recently about the methane bomb, which I don't know whether it's credible or not, but part of it is permafrost and the other part is methane trapped in the oceans. I haven't seen much mention of that. Is that a reality or not?
Shall I have a go?
I'm not an expert on this. I prefer not to answer the question if you know.
So we actually do quite a bit of work in the department on permafrost on land, working, again, using paleo records to try and reconstruct what's happened to permafrost in the past. Maybe I should start there by talking about the ocean, because this is an oceanic talk. There is pretty clear, there's a lot of methane locked up at mid-depth in the water in the ocean, in the sediments. And there is an expectation that as the ocean warms, that will be released. That cycling's been going on it happens naturally anyway, so it's quite difficult to really assess whether there'll be a significant increase in that release. And that's the sort of pivotal question. If it comes out very slowly and dribbles out, it's not too much of a problem. If it rushes out, it could be. And the best assessments that have been made so far, including those that are written up in the IPCC, suggest that there isn't an expectation of catastrophic release. But I think that's sort of a long tail risk. There is a very small chance of there being dramatic release from the ocean. I think we're more confident there will be release from terrestrial environments, but there's not that much there. So unless it's released very, very quickly, it's probably not too much of an issue. It's a positive feedback, not a catastrophic one.
We've got time for one more question. I'm going to ask mine then. It strikes me, as a communicator, it strikes me that the images that you show of potential damage to Europe in terms of inundation are very, very powerful and probably easier for people to grasp than emissions, because you can't see emissions. Why do you think it is that people aren't using those sorts of images more to communicate the point that climate change is happening and we need to do something about it? It strikes me as strange that we're not using those type of images more, that instead we focus on talk of emissions, which I do think is sometimes quite hard for the general public to grasp.
And likewise, a related question we sometimes ask is why we don't talk about ocean warming, which is what's actually happening.
The thing we've actually got control on is emissions. I suppose there's an instinct to bang on about that. I think you can make that question more compelling to people. One of the analogies I use as someone who owns a car is that I fill the car with petrol, I don't know, 50-litre tank, and then when I fill it up again, a week or so later, where's the 50 litres of stuff gone? It's in the atmosphere. And everyone's doing that. When you drive on a busy motorway, you look at the cars around you, all the cars are doing that. And I don't know if anyone had the experience of going to Didcot power station before they pulled down the coal-powered one, the sheer mass of coal that was going into a power station like that and then just disappearing and then going up into the atmosphere is quite compelling, actually. So I think you can make emissions, you can bring it home to people, but perhaps we should also be using images of damage more.
I think if people can physically see their land, their territory, disappearing like that.
My nervousness, and it isn't any different to the global warming problem, which is that actually global warming, in reality, some places will get a lot warmer, some places will get a bit warmer, some may even cool. And for sea level, that is also true. The regional changes are likely to be pretty substantial. And one thing Gideon didn't say is there's quite a lot of spread in the model projections for regional sea level change. So that's an example where the models at the moment are not so reliable. So I'm a little cautious in that, I think it could cause us problems downstream then when people say, well, where is the sea level rise you talked about in our part of the world? Global sea level will increase, no question, but one particular point on the coastline there's a lot more uncertainty.
Great. Well, I think you'll all agree that was a fantastic talk. Before we thank Gideon and David, I'd just like to flag up some events we've got coming up. For those of you who come every week and watch online, you'll know about them. But we have Dame Sally Davies coming on the 2nd of March to talk about antibiotic resistance. Obviously another very key issue that's in the media a lot at the moment. Just to let you know, that has been moved to the exam schools because the demand was so high. So if you've already booked or you're thinking of booking, it will be over in the exam schools. And obviously this seminar series continues, so please do keep coming. I think the discussions this term are really good. The questions from the floor are fantastic, and I hope everybody's gaining a lot from them. So if you'll join me in thanking our speakers today, it's been really, really informative.
Hello.